Lucene with bulk collection. So I'll just go about it again. So I did this already yesterday. My name is Ankit Jain, and I'm still a software engineer with AWS OpenSearch. I'm still a maintainer for OpenSearch open source project and a committer with Lucene. And really glad to be surrounded by such a smart, supportive, and vibrant community. So this is our agenda for today. We will quickly talk about the background. We'll try to understand the problem, how aggregation works in Lucene and OpenSearch, the journey of optimization, how it came about, some of the limitations of that approach, and then in the end we will also try to look at this whole process from a community angle, how strong collaboration and engagement with the community can drive shared growth and success. I know that this talk is not about OpenSearch, so I will keep this super short. So OpenSearch is an open source Apache 2 licensed distributed search and analytics engine based on the Lucene search library and originally forked from Elasticsearch. It offers a scalable, community-driven platform for real-time monitoring, log analytics, and website search, among other use cases. So we want to, I don't know why it is like this, but yeah. So aggregations are a really good way of understanding the data at a high level without getting into too many details. At a high level, OpenSearch supports 3 types of aggregation. There is metric aggregation, which is used to calculate stats like min, max, sum, or average. There is bucket aggregations, which is used to group and count documents like by date, term, or range. And then there is pipeline aggregation, which is used to build on top of other aggregation, using the output of one aggregation as input to the other. So it's very similar to a pipe operator in shell, where you use the output of previous command as input to the other. For today's talk, we will mostly be focusing on bucket aggregations, where we have seen some of the biggest improvements. So one of the most common bucket aggregation type is date histogram. Date histogram is widely used for many cases. For example, analyzing web traffic patterns, monitoring application metrics and logs, visualizing sales trends, and many others. So this visualization here shows a date histogram aggregation on a weekly basis for about 3 months of data. And so I think it's very easy to draw insights from data using this approach. Now, one of the things with aggregation is whenever we are doing aggregation, it is generally with a large set of data. We are not looking at 10, 15 documents, right? We are trying to look at data as a whole, right? So it's generally used for large scale analytics. And the way aggregation works in OpenSearch and Lucene, so it has a very, document at a time model. So let's say if you are matching tens of millions of documents, you will be processing them document by document, which can be really slow. So that's where we came up with the optimization for bulk collecting that. I'm sure most of us are aware of bulk storing in Lucene, but I don't know how many people know about bulk collection.
I would say a little bit about it. It's not a well-known topic.
Yeah. Okay. Yeah, that's good to know. So this is one of the queries that we'll be focusing on for a bit today. So this is a very simple query taken from NYC taxi dataset. So the query is on a field called drop-off date time. So it is just trying to filter the documents for 1 year from 2015 January to 2015 December. And then there is an aggregation on top of it, which says, okay, I want to know the number of documents for each month, right? So when I first started looking at it, I was like, okay, this is a very simple query. After all, we are just asking for 12 data points, right? So we want to just know the number of documents for each month. But it turns out when I ran this query, even for getting those 12 numbers, it was taking around 8 seconds. So I had a very simple setup. I just indexed the data on a single node instance in a single shard, which is nothing but a Lucene index. So, and I was very surprised to see that even for computing such a small thing, it was taking like 8 seconds. So that is when I was like, okay, let's try to understand this better. So, I don't know what happened here, but so that is when we started looking into this bit more, and we realized that at a high level, whenever we want to do aggregation in open search, right? So let's say we have a simple query. If we are looking for documents where status is 200 and operating system is Android. So Lucene will try to create a doc ID set iterator for status equal to 200 and for operating system Android. And then it will just try to intersect those two doc ID set iterators and create a new doc ID set iterator which contains result for both those queries. And then on top of that, you can run a collector to aggregate the information. And so here we will just iterate over the doc ID set iterator, document at a time, and then we are able to build really cool aggregations on top of it. So this approach is very simple, but it is very efficient because what it allows you to do is stream the documents through multiple level of collection. So you can have like 10 collectors. So at top level you are doing a date histogram, and then you will pass the same document through another collector so that you can build really cool sub-aggregations. So, and it uses the Lucene, like there is this doc values in Lucene which get used for building those aggregations. So one of the things, because whenever I'm looking into a performance optimization, I just try to run the query in a loop on a single node instance and try to collect flame graph from it. Because when we run it in a single on a single instance, right, that is the only thing executing on that node. And flame graph is a very good representation of where the time is being spent for that query. Like what are the different code paths which are expensive. And that is when it again confirmed our theory that since the processing is very documented at a time, the collect is the one which is taking most time. Not because individual collection is expensive, but because we are just collecting so many documents, one at a time. So these were the two primary limitations we identified. Okay, so I was like, can we do something better here? I mean, after all, we are just looking for 12 values, right? And it should not be taking this much time for just counting the number of documents. So one of the initial attempts I did was to I partitioned it into two queries. So I said, okay, let me get the response from January to June as one query, and then July to December as another one. And I can try to run them concurrently and see if that improves the latency. And because these two are mutually exclusive responses, the aggregating them together is very easy. You just take them, you take the 6 values from one and 6 values from another and fuse them together. So when I ran it, I was able to reduce the time from 8 seconds to 4 seconds, but as I don't know who this guy is, he pointed out that we are just using more CPU to make it concurrent, and it doesn't benefit when you have a high throughput workload, right? So it's essentially a zero-sum game, and that is when we are like, okay, we need to try something else. And so, okay, I think. So that is when we were like, okay, let's try to take a very small slice of this data, and what we will do is, let's focus on 1 month. I just want to get answer for the month of January, right? And I want to see how fast it can be. So I was like, okay, let me not run it as an aggregation. What I will say is it is a range query, and I want to track the total number of hits. I don't want any raw documents. I don't want any aggregation. aggregations. And I was surprised to see that I was able to get the same answer within 150 milliseconds. And that is when I was like, okay, so for 1 month, it just took 150 milliseconds. So even if I do it for 12 months sequentially, it will be like less than 2 seconds. So we are already down from 8 to 4 and 4 to 2 without increasing any concurrency. So this was like, done, this is it. So we can leverage this to really improve the performance. And this is where I will hand it off to Bowen, and he will take us through some of the meaty stuff.
Yeah, hi everyone. Just a quick introduction. I was able to find this photo of me with this capybara.
We want to know about that animal.
It's a giant hamster.
Yeah, I think this is a trip to Tokyo. They have a capybara cafe, and you can just buy a drink and sit with this chill guy for 1 or 2 hours. So, yeah, a little bit about me. I worked for AWS Open Search team. And previously I worked on a plugin called index management, and still a maintainer of it. And for the past 2 years, I started to working on the search performance and search features in OpenSearch Core. And Ankit has been a good teacher to me since the beginning. And this work we did brings me here, and I'm really grateful for that. Okay. And now let's go back to the content. Ankit just showed the aha moment we had. We can use this range filter query with size equals to 0 and track total hits equals to true to get the same document count for one bucket. We named this operation the filter rewrite because the filter here refers to this range query, and rewrite means it's rewritten from the data histogram. So different interval from data histogram will be rewritten to a bunch of such kind of queries. This queries is much faster compared to when you do the aggregation. It may finish, like I said, 100 milliseconds, or even just a few milliseconds, depends on whether you hit cache. And why it is so quick? Let's go back to this API from Lucene, count. This count API is, I think, a method in Lucene wait, and different query can implement it. So by default, it returns -1. But if you implement it, you want to provide a sublinear implementation that can return you an accurate number of how many hits you will have for this range. Yeah, and the point range query here, where we're utilize BKD. I think another guy from our team already talked about BKD yesterday. It's a quite interesting talk. Dive deep into the encoding decoding part. But now we just focus on how we use its structure during the search time. Still a quick introduction. So it's KD tree, k-dimensional tree. Here is a two-dimensional example. The first is split on the vertical dimension, then the horizontal dimension. Trying to keep recursively doing this, partition the space into smaller and smaller cells, and keep the documents or the data points in each cell relatively even. I think same number of documents across different cells, and then in the end it will create a hierarchical structure. So at the search time, you can very efficiently prune the cells that does not overlap with your query. And here's a very simplified model of BKD of just one-dimensional numeric data. Since the query we are looking at the data histogram, working just on the date field is a one-dimensional numeric data. This is kind of like the mental model we normally think about when think about how we traverse and doing the visit logic. using this Lucene provided interface of PKD. So the round nodes here are the internal nodes, each with 2 children here. You can imagine that they have the access to some metadata of this cell, like the min-max value, the boundary, and how many documents are in these cells. The rectangular nodes at the bottom are the leaf nodes. So only the leaf nodes, you can see, have the access to all the actual documents, IDs, and values. Internal nodes doesn't really have it, so you need to visit leaf nodes to actually see all the actual values of each document. By default, each leaf node hosts 512 documents as a block. That's our name, block KD tree. And this block is written to a different file compared to the index. So now we quickly walk through a query how we traverse this index and tells how many documents matches with this query. There's 3 relations if you when you traverse the tree. So the relation between the cell, the nodes you're traversing, and compared to this range query. It can be, so here the range query is starting at 351. So compared to the first nodes, the 180 nodes, so the cell itself is not inside the range, and also it's not fully outside the range, so that's the third relation is a cross. If it's a cross relation, we will traverse down the subtree, left first, then go to the right. We'll go to the first left node, 1 to 400. Still, I think it's a crossing relation, so we keep going down to 1 to 200. And this one is outside the range, so that's the cell we can prune. We don't need to keep going down. And then go to the right one, 201 to 400. So the left tree is still outside of this range, but the right node of this one is a leaf node. Starts from 301. So it overlaps with the range query. So this time we need to actually visit these leaf nodes. So these leaf nodes have 512 documents. We need to visit from the beginning to the end, all the 512 documents. So in the end, starting this range from 351 to the end of this leaf node probably gives us 50 documents to the total counts. So apart from these leaf nodes, you can see the other one in the right bottom is the other nodes we really need to visit. So for this query, we visit 2 leaf nodes, and for the other nodes that are actually inside the range, so we only need to read the metadata. We don't need to really visit all those doc values. So now you can get a sense of why this is much faster than normal data histogram application, which it will need to visit documents one by one in doc ID order and read the value and do a rounding so it knows which bucket it belongs. This way we actually skip a lot of that, so it's like a bulk collection. So in the end, we can rewrite that data histogram, monthly data histogram, to this kind of multi-filters query. It's just to give you a sense of all these filters we are rewriting. And to summarize, what we are doing here is before the execution, based on the data histogram, we will create a bunch of range filter, which is also the buckets, the boundary. And from this bucket, we will create those point range query, quick wait for it, and use that count API to quickly get the number of documents of that range. Let's skip a lot of doc value tree. Here's our results. You can see that we released this feature in 2.12, and suddenly this high bus basically went away. from 4 seconds to maybe down within 100 milliseconds. So I think up to 50 times improvements using this technique. The minute aggregation here, you see, is not improved a lot. As compared to the hourly and daily, minute aggregation actually creates more buckets, or more of those ranges, and it actually has more overhead. And another thing we got report is after releasing, there's actually a regression. So we did this benchmark on NYC taxis, but some other from the community people report that on another data set called PMC, they actually observe regression. And that data set is a data set of articles. And every document has a timestamp. So it's a little, compared to NYC, it's a very sparse data set across 10 years and only have 574K documents. So there are total 123 buckets if you do a monthly aggregation. So same technique, we do a profiling, and we found out this visit doc values method provided when you do the PKD traversal actually takes most of the time, around 83% of the CPU cycles. So what is the visit doc values? That's the method will be called if you have to visit that leaf node. So we know that most of the time we're spending traversing the leaf node. So now the question is how we can optimize this. Right? There's a quiz time. So for one-dimensional BKD with total of 2 to the power of 10 leaf nodes, how many leaf nodes do you think are skipped when we do a range query?
It depends on the range.
It doesn't really depend. It depends on range, but we think about the worst case. The worst case.
0. Worst case. Skipping.
Are you asking skip or is it
Skip.
Yeah, you can also think of how many leaf nodes have to be
Well, if
visited.
you have 512 in each bucket, that's only 2 leaves, so you have to visit all of them, basically.
Yeah.
Yeah.
So at most 2. This is only one dimension. 2 leaf nodes at most. But when we are doing a lot of range queries, like n range queries, so total we are actually visiting 2n times of. So it's kind of a waste because we are actually double counting many leaf nodes with it. We don't have actually need to visit all the leaf nodes for the range query 2 times. And that comes this kind of new customized traversal logic to solve this inefficiency. The goal is we think, why don't we just do one traversal, right, and populate the results for all the ranges. So here is a same diagram, the same BKD diagram as before, but now we have total 4 ranges. The first thing we do is we can sort these ranges by starting time. And let's start from the first ranges. We start from the root node and go down, and the first leaf node is actually fully within this range, so we count that. The second leaf node we need to is crossing, so we need to visit that node. The same thing. Oh, and now the second leaf nodes end at 200, which is larger than this range's upper bound. So that's how we know that for this range we're done. Right now we can move to the next range. For this range we don't need to care about it anymore. So now we go to the next range, starting from 201 to 301. And to handle that, it's the same. We still continue from this traversal, because all this BKD saves based on the doc values is in ascending sorted order. So we can just continue the traversal, go to the sibling node, which here is 201 to 400, and we now handle the second range. So go on to the third range, fourth range. And this way of traversing it, you see, we are now only do the single traversal. Previously, how many buckets you create, you need to do that many traversal. Although it may not be that much cost to just traversal, but we save some cost here. And more importantly is that we don't really can visit leaf nodes, any leaf nodes twice, the same leaf node twice. Right? We are only, at worst, we're just visiting all the leaf nodes. And the tricky part is visit the leaf nodes of this BKD tree. Seems to be a little bit cheaper than just visit the dot values. The actual reason may be very deep, but that's how we see from our experimental benchmarks. If we revisit our previous results, so this is actually released, this new techniques released in 2014, and that's when the minute aggregation also goes down. So it really helps with aggregation with a lot of buckets. And if we zoom in these results, you can see even the normal, previously the hourly and minute also benefit from this technique, right? So that's how we know that we really save some traversing costs also from this. Yeah. And now handing back to Ankit, who will talk about the Lucene contribution.
Can I ask you a question before you? Can you handle overlapping ranges? No.
Currently, we are not handle.
Seems like you could.
Yeah, we could. So the data histogram, you see, is not overlapping when we rewrite it. But there's also range aggregation. You can absolutely define overlapping ranges, but we haven't supported it. We can.
Thanks, Bowen. Thanks, Bowen, for walking us through the optimization. And actually, I think that was one of the things I was going to mention, that it works only for mutually exclusive ranges, right? We have not handled the overlapping case because it can get really tricky. You need to keep, a lot of bookkeeping to ensure that you know which are the overlapping buckets currently. So, yeah. And I think Bowen did mention that, when you're iterating over the BKD, we are essentially doing an in-order traversal. So that's why, once you are out of a bucket, you are not going to find any more points which will get into that bucket. So I think after we did this optimization in OpenSearch, we wanted to contribute it back to Lucene, right? And we were able to do it this year, 4 or 5 months back, we contributed it back in Lucene as well. And Adrian tweeted about this as well. This was a really cool optimization. And so one of the things I realized, when I was working on this optimization, even though I had a PR open for a bit, but I was unable to get a lot of traction on that. And that is when I was even I did mention that we saw some improvements in OpenSearch, right? But I did not have a Lucene Util kind of benchmark to show that the performance improved this much. And so that is when I went ahead and thought, maybe I will write a low-level JMH benchmark for this. And I wrote that, I collected some numbers from it. And the moment I published it on the PR, it got more interest from the community, and they were like, "Oh, this is really cool. So let's go ahead and merge this PR." So I think one of the limitations that we have over here is of this approach. So if there is a multi-filter aggregation, so essentially you have more than one filter, or maybe filter on some other field than the one you are aggregating on, we cannot leverage this optimization because there is no correlation between that field and the other field. The BKD is just on the aggregation field, and you are not leveraging the top ID set iterator that you created while executing the query. Also, if you need to do sub-aggregation, you have to visit those documents in context of that bucket so that you are able to, read the values for those.
But if you had a multi-dimensional KD tree, couldn't you do the sub-aggregations? Or is it only 1D optimization?
So this one is a 1D optimization.
Okay.
So yeah, I was thinking about it a bit. I'm not really sure whether we can do that or not. I mean, you have to be able to total order it. You have to be able to say, okay, because we rely on the in-order traversal.
You can do like bounding box subdivision. Like you could start excluding large parts of your tree, right?
And there is a way to total order a 2D space, like the Hilbert transformation, you know, that
Yeah.
crazy curve. That's a way to put a distinct order, reproducible order, and dimensional space.
But this is not solving this multi-filter problem, right?
Right, I'm talking about the second bullet, sub-aggregations.
Sub-aggregation.
Yeah, okay.
Yeah. And also, like if there are deleted documents, this traversal does not account for that. So in those cases, we have to fall back to the flow approach. So at least for multi-filter aggregation, one of the things I realized was we can use the skip index. So this is a fairly recent feature, like probably, you know, I think it was in 10.x that we introduced this. And so there is a special case here. Let's say your index is sorted on some field. In those cases, the doc ID and the doc values for that field are proportional to each other. So higher a doc ID, higher the value for that doc ID for that field. So how we can leverage this fact? So we looked earlier that, you know, whenever we want to do an aggregation, we first create a doc ID set iterator. And one of the properties that doc ID set iterator has is they are sorted by doc ID. Now we will be able to leverage that property to like if the aggregation is on the field which has skip index, we can leverage that property, right? So what we can do is we can while we are iterating, so let's say there is this doc ID D that we are looking at, and we say, okay, this doc ID D falls into bucket B, right? And for the same bucket, the upper bound is something B dash, right? Now we can tell, okay, this B dash value, where is it in the skip index? What is the maximum doc ID for which, until which we can find B dash? And now what I can say is, okay, this is the doc ID in the skip index, until which I can collect all the documents in this iterator in the same bucket, right? So
Is this like calling advance on the iterator?
yeah, advance.
Yeah.
So we, like on the skip list, we are trying to find the highest possible level or maybe lowest possible level so that we are able to skip as many documents as possible. So this approach is like slightly better because this is more generic in nature and fits in directly with the doc ID set approach, this doc ID set approach that we have for doing the aggregations. And initially I thought, okay, even if we are doing this, we still need to count the number of documents in the doc ID set iterator, because the skip index is saying, okay, all the doc IDs from this to this are in the same bucket, but the doc ID set iterator is a subset of that because it filtered on some of the fields. So I still need to count the actual number of documents in the doc ID set iterator, and that's where I saw this thing. So there is this pop count instruction, right? It's a CPU instruction. It's a short for population count, which can be used to efficiently count the number of set bits in a word. So using this, we can, so if you, like you have a stream of doc IDs and you want to count the number, we can do this very efficiently. So we ran some preliminary benchmark using this approach.
Wait, where do you get the bit set from? Doc ID iterator, I assume you can call next, you can get the next doc ID. But if you want to get a bulk bit set.
So I think when we use the collect method, so I think there is this individual doc ID and then there is a doc ID stream. So the collect is also able to pass you a doc ID stream, right? So in those cases, you can say, like if all the doc ID stream falls within that range, you can collect them using the stream.count method.
Okay, I have to read that.
Yeah. So
Bulk
we ran-
collector, I guess.
Sorry.
That's a bulk collector interface? Collecting a stream instead of an individual document?
Yeah, technically. So we ran some preliminary benchmark on OpenSearch. This is like not contributed even into OpenSearch yet. This is in POC. And we saw that it is up to 3x improvement. And like I was actually like looking through some of the issues and I noticed that this is a optimization we kind of picked from TanTV, right? And we used this optimization in Lucene, and then Adrian opened the issue with TanTV saying that okay, we can use this optimization to do some of the other cool things as well, just in case you want to do that. And this is where I realized, like while we can look at this purely from an engineering perspective, that we saw okay, there is a problem and there is something better we can do, and we showcased like some results. But we can also look at it from a community lens. So when I started on this problem, I was not aware of how the count method in range query works, right? I was just trying bunch of things, and I noticed, okay, this seems very fast. I want to understand it. And when I understood about it, we were able to implement something better on top of it, right? We implemented multi-range traversal, which was a very good optimization. And we went, like, even though we pushed it in OpenSearch last year, we weren't able to get it into Lucene until early this year. But when we contributed back into Lucene, I was going through that histogram collector that we have in Lucene, and I noticed that there is like another way of collecting, which is using skip list. So I was not aware of that before. So when I went ahead and actually contributed back, that is when I learned about leveraging skip list for histogram collection. So that is where I realized, like if I had not contributed back into Lucene, I would not have learned about this another optimization. So contributing back actually gave me some more ideas, and I am able to address some of the limitations that we have for collection right now.
One other tie-in, I think the sublinear count API was also inspired by TanTV. The whole notion of sublinear counting required a new set of APIs in Lucene, which I think then resulted in this efficient range query count.
Yeah.
So there's a TanTV pre-tie-in to all of this as well.
Oh, I was not sure about that one.
Okay, I'm not sure either, but I'd like to double check it because I think sublinear count was inspired by TanTV.
Got it. Because at least the initial one we leveraged the count for range query, which should be using DKD.
Right, but I think the notion of a count that could operate in sublinear time was at TanTV for other queries, normal queries, resulted in an API change to Lucene where we put the count on wait. Adrian had to make an API change, which then caused Lucene developers to look around at other queries that could be sublinear counting, like KD tree queries.
That must be, I don't know, sometime back, or is it something recent?
Yeah, TanTV wasn't too long ago, right? 3 years ago? 3 years ago? We had a count method, but for some reason it could not. It was in the wrong place to be sublinear. There was some reason, or was it
The
defaulted
index
to cost?
searcher had a count method.
You're
right.
The BKD's count is different. The mechanism is different from the sublinear count, which is essentially
It is.
relying on the bit set.
Right, but I'll have to go back and check the history, but I think the notion of sublinear counting was inspired by TanTV on not BKD queries, ordinary queries, postings list queries.
Yeah.
And
Yeah, that one is
down.
right, but that resulted in an API change in Lucene to expose a count API, which is allowed to be sublinear, which caused Lucene people to look at all the other places where we could do sublinear counting, resulting in KD tree being a great place to do sublinear counting, resulting in this whole series of things that led to this. I think that's a chain of events, but I'll try to double check it. It's a good open source story.
Yeah. So some of the other things that I learned, and these are like again very recent, so in last few weeks, so I think there have been like a lot of PRs in Lucene around writing things slightly differently to take advantage of JVM inlining, right? And bitwise execution. So we want to, like, instead of iterating over document at a time, we want to do batch at a time, right? And this has given, like, again, some other ideas which we can try for optimization in OpenSearch, especially for computation of scalar functions, right? If you want to just collect the sum over a bunch of documents, instead of doing it one by one, we can like load the values in a buffer and use that to compute it faster. So these are some of the related links. I think I missed the one on Lucene, but we can. It should be easy to figure out. I don't have those many PRs on Lucene yet, so thank you.
Thank you.
Any questions?
Yeah, just want to make sure I understood where some of this was happening. There was a reference to it in Lucene. There's a reference to a histogram. Is there stuff here that you're referring to in the faceting module, if that's what it's called? I forget if it's even called that, or no?
Right now it is in sandbox module, that histogram collector.
Okay.
So yeah, ideally it should get into faceting, right? But I think it's more experimental. So yeah.
Okay. Thanks.
Yeah, and I don't think that it overlaps with the faceting API.
Exactly.
Yeah.
Okay. Thanks.
Which maybe is better for solar because it has its own faceting API.
Yeah. Thank you.
So recently I've been thinking about like OpenSearch has like such rich aggregation framework. How can we like get more of it into Lucene? So I know like Lucene is not positioned as a log analytics use case, and it's mostly search use cases, but yeah.
Yeah.
Cool. Sorry.
So the deleted documents case, it's kind of frustrating that the optimization falls over in that case. Do you think there would be a way to do a one-time walk of the KD tree to get the counts minus deletions? Hold that on the side, and then when this optimization kicks in, it would work with deletions?
Like,
Yeah.
sorry, I did not exactly
Count the live docs in each bucket.
got it.
Because when your optimization is really powerful, is when it can skip a whole leaf node, or many of them, just accumulating counts. And so if we knew the count minus the deleted documents of those leaf nodes, you could continue to skip them even in the presence of deletions.
But in the case when, so like when I'm skipping a leaf node completely, right? I don't know like how many deleted documents are there in the subtree, but we can maintain that. Is that what you're saying?
Right. What I'm saying is doing a one-time walk of the KD tree on refresh. It's per reader refresh, so it's order n. There's some cost question there, but every refresh, do a one-time walk of the KD tree to compute the counts incorporating deletions.
Yeah, that's a good point.
So then every subsequent query would be able to use the optimization.
But I'm wondering, do we like probably need to write the tree again?
I would just do it in memory. I wouldn't try to write a new tree.
Got it.
You would just have a little data structure on the side that says, here are the counts incorporating deletions.
The tree could do it itself when it constructs itself from the reader.
We do it when we.
When you read the information, it could just it could
Yeah,
do that.
yeah,
I don't
if it's
know, or it
sort
could
of
be another
generically
version
useful.
of it, like a,
Yeah.
you know.
The downside is it is a linear walk, right? You have to walk the whole order n. Every document has to be checked in the tree. Per refresh, there's an order n cost. So there's that upfront cost. So, but if that's offset by enough date histogram queries, it's totally worth
If you
it.
can get a bulk, if you can get bid sets in bulk of the doc IDs in your tree, you could intersect them with the live docs bid set, and then it would be faster than linear. It would still be linear.
Yeah.
And
PopCap.
another
You can
thing-
use the PopCap, right?
Yeah.
Another thing I was thinking was like maybe you just collect as if there are no deleted documents, and then you iterate over the deleted documents if it is a small set, and then like is there a way to still read the doc values for those documents? We can, right?
Yeah, I think so.
So you read the doc values and kind of correct, okay, this bucket, these documents were accounted for.
Yeah, that's a good way to do it too. So then it's order number of deleted documents, which could be a lot smaller
Yeah.
cost. Yeah, I like that solution too. I would open an issue and get some discussions around here, because deletions, it's disappointing if you delete one or two documents, suddenly the optimization falls off a cliff and your queries are a lot slower.
Sorry, Vinod.
Yeah, but how about like if you have like multi-valued docs and there would be two docs having the same value, right? And you deleted one but not the other one, but that might still be in your bucket.
In Lucene, you have to delete the whole
That might
document.
count as a deleted doc, but it might still appear in your bucket, right? And that value might be present in some other doc.
But when the doc gets deleted, both values would be, they're both deleted at once, right? We can't delete individual values of one document.
Yeah, what I meant to say was like if one doc is deleted, not the other one.
two docs have the same value.
Yeah, have the
I
same.
don't think that's a problem here because you subtract the count, you subtract one from the count of that value.
No, I think he is asking about one doc having two values. But even in that case, right, so from the doc values you figure out, okay, this is the doc ID and these are all the values that were deleted along with it. So we can like iterate over all those values
Sure.
and
Yeah.
each of the bucket mapping to those values will be
Okay, yeah, I think I understand.
yeah. Although I think
Right,
we don't
sure.
apply this optimization in this case when we have like more than one value per document, because if both those values are in the same document, same bucket,
Yeah.
then we will double count that document. So, right?
Tricky.
What about, I want to know, is there any room for probabilistic algorithms here? I feel like if you don't care if your counts are precise, you're willing to tolerate some error in the counts. Maybe you can do faster counting. I don't know. I don't have a good idea about it, but just think about it. Because a lot of times people don't care. They're doing these aggregates, they're looking at graphs. You could tolerate a 1% error and it wouldn't really matter. And you can correct it if you zoom in, right? But sometimes if you let yourself have a little bit of noise, then you can make it nice up.
I get a bit picky when it comes to the correctness.
Yeah.
So I'm like, if I want to know that this is correct, so yeah. But I'm sure like most of the cases like approximation also works.
Linking is using a sampling algorithm for the facet counting, and the result varies depends on the update pattern. Sometimes your updates are just coming in the cluster, and you got a very bad estimation on the facet.
Yeah, but I think here.
All right, thank you.
Yeah.
Yeah.